Measuring heat flow. We measure it in calories. A calorie is defined as 1 gram, the amount of energy it takes to change the temperature of 1 gram of water by 1 degree Celsius. So the units of heat are defined in terms of how much energy it takes to heat up water, or cool down water for that matter. Okay. Now we also measure heat flow in joules, but joules are defined in a physics sense as the amount of energy it takes to move 1 Newton of matter by 1 meter. So that's why this number here is not a nice whole number. So we could, if we look at joules in terms of the amount of heat it takes to change the temperature of water, 1 gram of water by 0.239 degrees Celsius. Now, in terms of food, dietary calories are actually kilocalories, which is 1,000 calories. So 1 dietary calorie is 1,000 calories, or 1 kilocalorie. Now, the conversion between calories and joules. 1 calorie is equal to 4.186 joules, or if we use joule as a standard, then it's 0.239 calories. Now, one of the things that's confusing about the heat unit is that there's a lot of terms that are similar but different, like heat and hot are similar but different. Heat capacity and just regular heat are similar but different. Specific heat and heat capacity are similar but different. So I'll do my best to try to make them make sense. So heat capacity is the amount of heat needed to increase the temperature of a substance by 1 degree Celsius, which sounds an awful lot like the definition of a calorie, but this is for any substance. Now, heat capacity depends on the amount of substance, its mass, and the properties, the chemical composition of the substance. So iron, a nail might have a certain amount of heat capacity in it, and a steel girder made of the same material would have a different heat capacity. Even if that nail were sitting on this girder, they might have the same temperature, but they have a different heat capacity. For instance, if this were a really hot day and while these workers are eating their lunch, I imagine that steel girder is remarkably uncomfortable to sit on. Whereas a nail, if it were sitting in that same sun and you were to hold it in your hand, it wouldn't be nearly as uncomfortable to come into contact with. Okay, so the higher the heat capacity, the more energy it takes to change the temperature of a substance. So, in Florida, when there's a forecast to have a frost, one thing they do is they spray the trees with water so that the water will freeze instead of the oranges. Okay, one of the most dangerous forms of food to eat, if you've ever eaten a hot apple pie or a hot pocket, and you feel the crust and feel, oh, that's safe to eat, I'll go ahead and bite into it. And then you bite into it and the molten substance inside burns the roof of your mouth. That's because the heat capacity of the crust is low, the heat capacity of the molten interior is high. So specific heat is similar to heat capacity but different. It's the amount of heat needed to raise 1 gram of any substance by 1 degree Celsius. So one author describes heat capacity as thermal inertia. And inertia is the resistance of change in motion. So if you push on a substance or an object with a lot of inertia, it's hard to push and it's hard to slow down. In the same way, if something has a high specific heat, it's difficult to change its temperature. You can try to heat it up and it'll absorb a lot of heat, but its temperature won't change that much. So water is a substance that has a high specific heat. So if you've ever been in a hurry to maybe make a cup of tea and you're trying to heat up the water and it seems like it's taken forever, That's because water has a high specific heat. It's hard to change its temperature. Now, we call it specific heat because each substance has its own specific heat. So water has a specific heat, iron has a specific heat. It doesn't matter how much of that substance you have. It's a constant for each substance. Okay, so here's a table, and if you notice, water has an unusually high, let me get this out of the way, has an unusually high specific heat. Okay, if we look at iron, it's way down here. Water's almost 10 times greater in its specific heat. So if you heat up 100 grams of water and 100 grams of iron, you're heating them up the same, but the iron will get a lot hotter than the water will, which is hard to get your brain around. You're heating them up the same, but one is changing temperature more than the other. So if we're trying to calculate the heat flow, Q is heat, so we can see that heat flow involves three different properties, three different quantities. So it depends on the mass of the substance, the specific heat of the substance, and also the change in temperature of the substance. Okay. So let's go ahead and look at a calculation. Say we take a hot pebble and we drop it into 20 mils of water. It's 22.5 degrees. And the water temperature changes from 22.5 to 24.3. How much heat is given off by the hot pebble? Now, if you look at this, you think, well, I don't know anything about the pebble. I don't know how big it is. I don't know its specific heat. And I don't know how hot it was. So how can I do this problem? Well, if you remember, the heat given off by one thing has to equal the heat that is gained by the thing it's in contact with. So if we just switch the energy released by the pebble, we know that it's going to equal the energy absorbed by the water. So let's just use all the information for the water and then go ahead and do the math. So the Q for the water, the amount of heat absorbed by the water, will equal the 20 grams of water. Oh wait, no, this says 20 milliliters. Well, you remember the density of water is 1 gram per milliliter, times the specific heat of water, which is 1 calorie per gram per degree C, times the change in temperature of water. 1.8, where did I get that from? Well, you take the 24.3 and you subtract 22.5. You always take the higher temperature minus the lower temperature. Okay. Just multiply those out and you get 36 calories. Oh wait, but this says joules. Oh, okay. So all I have to do is take the 36 calories and multiply it by the conversion factor, 4.186 joules per calorie. So it's 151 calories. So the amount of water absorbed by the water from the pebble is 151 joules. So the amount of energy given off by the pebble is 151 joules. Now, heat change is always the same because of the law of conservation of energy, but the temperature change is rarely the same. So the water only changed 1.8 degrees. How much do you think the pebble? It was hot. How much did it change its temperature? So the reason is, if you stop and think about it, the reason is the masses of the substances are different, but the main reason is the specific heat of the substances are different. Okay. So if the specific heat for the pebble is 0.79 joules per gram degree C, and its mass is a paltry 1.89 grams, so it's just a little bitty pebble, what was its temperature change? So how would we do that? Well, we get the energy from the preceding problem that we did. We know that it lost 151 joules of energy to the water. The mass of the pebble is 1.89 grams. The specific heat is 0.79. Excuse me. So then we just solve for delta t.